I'm going to prove kind of a more normalist function is integrable on 0, 1, and I'm going to do it much the same way that I did my last screencast. I'm going to let epsilon be bigger than 0. I'm going to find a partition such that the u of f p minus L of f p is less than epsilon. And to do that, I'm going to pick a little n such that, how about 1 over n is less than something. I'm going to tell you that later. The idea here is I'm going to pick 1 over n, 2 over n. I'm going to compare the triangles. So this would be u of fp in the black. We're going to look at a bunch of stuff like that. And in the red, I'll do L of fp. Right, L of fp is going to look like this. So I just want to calculate the difference between the two. Now I can do this pretty easily. So I'm going to calculate u of fp minus L of fp directly. And that's going to equal to the sum of I equals, how about 1 to n of x sub I minus x. Sorry, I did that wrong. I was zoning out there for a second. I'm not sure what I was thinking about. Mi minus mi, the supremum minus the infimum, times the length of the interval. Well, let's look over here. What's going to happen? If I look at two different intervals, the supremum for this first, in fact, let's even look at ones in the middle. The supremum for the first one in the middle, right, that's higher than everything else there, happens to be the infimum for the next one. So here it's the supremum, over here it's the infimum. So that's going to amount to, first of all, you notice that the right side is always the supremum and the left side is always going to be the infimum. That's because it's increasing. And we're going to get a log cancellation. So this is actually equal to I equals 1 to n. It's going to equal to f of xi minus f of xi minus 1, the f of the right endpoint minus f of the left endpoint, times the length of the interval I'm going to pick to be 1 over n, and 1 over n I define to be such. So this is kind of like what you did in Calc 1 always. You always just pick the intervals that have the same length. It is convenient to do oftentimes. So this is just going to be equal to I equals 1 to n of 2xi minus 2xi minus 1 of 1 over n. But if you write this out, what you get is you get everything's multiplied by 1 over n. Then you get 2x1 minus 2x0 plus 2x2 minus 2x1 plus that plus 2x xn minus 1. I'm screwing that up. Minus 2xn minus 2 plus 2xn minus 2xn minus 1. And if you figure this out, you go, hey, look, the x1 is going to cancel with the x1 there. The x2 is going to cancel with the x2 there. Figure out the x2xn minus 1 is going to cancel with 2xn minus 1. 2xn minus 2 is going to cancel with something over here. So what this boils down to is it all collapses down into, let's see, I have 2x1, or 2xn, sorry, that's an n, minus 2x0 times 1 over n. Oh, and x0 is always the leftmost thing, which is 0, and x1 is always the rightmost thing, which is 1. So that gives me 2 over n. So the difference between these two is 2 over n, and if I want this to be less than epsilon, I can pick this to be less than 1 over n is less than epsilon over 2. Right? This is equal to 2 times 1 over n, which is less than 2 times epsilon over 2 equals epsilon. So once again, we proved it. So this is a more standard way of using the integrability condition. So we can prove that this function is integrable by doing this trick. We just need to basically pick our delta x, as you call in Calc 1, small enough. Note this doesn't tell us what the integral is, it just says we can find the integral. Now we might want to use the fundamental theorem of calculus or some such thing.